Okay, first, let me thank the organizers for this great opportunity. So I'll be talking about Brownian non-Gaussian diffusion. By now, I think audiences are familiar with this word. But anyway, let me briefly and quickly set the stage for the talk. So when we say Brownian diffusion, the picture which will come to our mind, a Gaussian PDF along with mean square displacement, very linear in time. So it's a familiar picture. So, but let's see what more we can see other than this particular picture. So it's already shown in experiment that no, it's not always the case that one can have a non-Gaussian PDF like this along with the mean square displacement very linear in time. So people termed it as a Brownian yet non-Gaussian diffusion. So this talk is going to be going to give little details about this Brownian non-Gaussian diffusion. So with this very brief background, let me tell you in an elaborate way that what we are going to see in detail. So first we will see origin of Brownian yet non-Gaussian diffusion, and then we will see the origin from polymerization process, and finally I will briefly tell you the effect of non-Gaussian PDF on the survival characteristics. So these three are the main point. So let me tell one by one. Okay, so first we will see the central theoretical idea behind Brownian non-Gaussian diffusion. The central theoretical idea is a subordination. Basically, subordination means superposition of different diffusivity. I will tell you in a little more elaborate way. Suppose you take a diffusion coefficient which is time independent. So when you take a diffusion coefficient time independent, time dependent, so you can see that P of xt equal to 1 by root of 4 pi s into exponential of minus x square by 4s. So if I know that, if I know the trajectory s, you know the distribution. But what if the d is a stochastic? And when the d becomes stochastic, s also will become stochastic. The probability distributions then become average overall distribution, average overall realizations of S. Basically it means that, so it is Gaussian weighted with a this factor, and that factor is precisely controlled by the process S. So the summary is that P of xt is now weighted sum of Gaussian. But what is the consequence of weighted sum of Gaussian? So this is the weighted the consequence of weighted sum of Gaussian. So you can have a non-Gaussian PDF with MST very linear in time. So it's originating because of the stochastic D. And two more comment, when you have a narrow D distribution, if it's too narrow, then it's going to be a narrow distribution for P of st and then Gaussian. But the moment you have a large or a broadened distribution for D, it will end up in giving a non-Gaussian diffusion. So this is the basic thing. And with this background, let me quickly say the origin of non-Gaussian diffusion from polymerization. So polymerization, so during the polymerization, the number of monomers are vary in the chain. So it's a stochastic quantity. So as a result of this fact, the center of mass of the polymer chain will acquire a stochasticity in the D. So we have already learned that, seen that the stochastic D will lead to non-Gaussian PDF. The only question remains when this can show a noticeable non-Gaussian PDF. So it's possible when monomer distribution is broad. When monomer distribution is broad, you have a broad distribution for D, which eventually will lead a noticeable form of non-Gaussian PDF. In fact, that is possible when near critical point which separate dilute phase from dense phase. During that, you will get a broadened distribution for N, which eventually lead a noticeable non-Gaussian PDF. You can see that as we increase G, you have a very fat tails, or which is actually deviating more and more from Gaussian thing. So this is how you can get a noticeable form of a non-Gaussian PDF. So this is the origin of Brownian non-Gaussian from polymerization, and then we will enter into the last part, which I already promised. What is the consequence of this non-Gaussian PDF on the survival characteristics? Is there any interesting thing due to this non-Gaussian PDF? So basically consider a diffusive process with a non-Gaussian PDF with some observing boundary. The question is that such a thing is going to survive more or less. You can see from this graph, this dotted thing is for non-Gaussian tracer. So it's already the area is high, which is already giving information that this non-Gaussian tracers will survive more because this is more area. But that's not the end of the story. Little more thing. What we have to see, yes, it survive more. But if you look at this thing, there is some initial survival drop. What is the significance of this initial survival drop? The significance of initial survival drop is that suppose if you want to activate a function very quickly with very few tracers, very few tracers, and then the non-Gaussian is very helpful. It will reach target very quickly. But on the other hand, okay, if you want all the tracers to reach the boundary to activate a function, and then Gaussian is helpful because that Gaussian area is small, so it will reach quickly compared to the non-Gaussian. So that's the message from the survival thing. But let me quickly tell you why this is happening, or why non-Gaussian is helpful when we need a few tracers, or why Gaussian is helpful when we want a more number of tracers. It's actually coming from this very generic structure of non-Gaussian PDF. If you look at this thing, you can see a fat tail, and this is actually representing the faster diffusion, and there is some excess probability in the center, that is slow diffusion. So this is precisely due to the fast diffusers in the system. So when you have fast diffusers, definitely it will reach very quickly. So the reason why the initial survival drop is precisely because of this fat tail, and the why Gaussian is surviving more because of this excess probability in the center, which is actually slower diffusers. Okay, so with this, I will give you two important messages. First, monomer distribution broaden near polymer critical point, that will lead a noticeable non-Gaussian PDF. The message 2, non-Gaussian PDF can have an interesting consequence on the survival. Precisely, non-Gaussian diffusion is efficient for situation where a few tracers are needed to reach a target. And the second point, Gaussian is efficient when you want majority of tracers to reach a target to activate some function. And let me also quickly show some of the research interest I have. So this is reaction diffusion patterns on curved surface. That's also I am working, specifically trying to understand the preferential positioning of spot on different curved surface. Thanks ICTS for this great opportunity. I would also like to thank Fulvio and Flavio for various discussions and support. And of course, I also like to thank Vittoria and Alexi for many useful discussions about survival of non-Gaussian diffusion. So with this, let me stop. Thank you.
Question?
So when people talk about the non-Gaussianity in the let's say in the Van Hoff function, the kind of argument they put forward is the time of observation, the window of observation is short, then you get non-Gaussianity, but eventually it should be Gaussian.
Exactly. In the long time, it will be Gaussian. Why it's not going? Okay, sorry. I will tell you how. Yeah. So it's coming. So in the long time, this P of ST, it will peak around some particular, say, D star T. So when P of ST then will become delta of S minus of D star T. So when it is a delta thing, exponential of x square by minus of x square by 4 D star T, whatever it is, that's a Gaussian thing. So in the long time, this actually will lead to that delta thing. So but in the short time, yes, it's a superposition of Gaussian.
In case of polymer that you discuss here, do you see something very similar? Like if you observe for a long time, then
yes,
you
it will.
Yes.
Okay. Any other question? So let us thank the speaker once more.
Thank you.
And here we conclude this session. And thanks to all the speakers for their nice talks. Thank you. Bye.